So one of the great things about guitars, electric guitars, is you can get all kinds of interesting tones and sounds out of them. And if you play guitar at all, you probably know that there's almost endless arguments over where tone comes from and what it is. Whether it's the guitar, whether it's the amps and effects, or if it's your hands. And if you've been interested at all, Lill did a whole series of videos on guitar tone, and they are fantastic. You should check them out. But it sort of inspired me to take my own take on it. And I'm going to come from a little bit of a different perspective. I'm not a hotshot Nashville guitar player. I'm thoroughly mediocre. But what I do have is a very particular set of skills. I'm a tenured professor at an R1 research university. I teach graduate level courses on computer science and optimization, things like that. Do a lot of integrated circuit design sort of things. So going down weird technical rabbit holes is kind of my jam. And so I'm going to come at guitars and things like that from that perspective. Trying to nail down the physics, the math, is exactly what's going on to make things sound this way. I'll try to keep all the math from being too gnarly and too scary. It's actually not too bad once you get your head wrapped around it, and really interesting and a lot of fun. So let's dive in. All right, so back out of the flying monkey suit. It's hard to play guitar with puffy sleeves. I'm going to start off and get very precise by what I mean by tone. I've got American-made Fender Telecaster here. I had this guitar since about 1989. Bought new at Grandma's Music in Albuquerque. Grandma's gone, but the guitar's still here. And so for consistency, I'm going to be using an amp simulator, not an actual amp. I'm using DB AudioWare's 20th anniversary. Gives me a consistent tone, so I can, every time I fire it up, it's going to do exactly the same sort of thing. And when I need to, I'm going to be using a Clayton pick, 0.63 millimeters. Grab that guy. So Clayton pick. Again, trying to get consistent tone, consistent sound, keep things as much the same as I can. So let me start off here and I'll nail down exactly what I mean by tone. Here's an A. This is on the neck pickup. If I switch to bridge, you can hear that they're different. Tone of this is different. And so when I say tone, this is what I mean. This versus this, or middle position. It's all kind of subtle, but it's definitely there. If I was to swap this for a Les Paul or a Strat or something like that, different guitars do in fact sound different. And that's what I mean by tone. And so what I'm going to try to dive into is the physics, the math, exactly what's happening and why. So when I pluck an A string, and go back up here to the neck pickup. When I pluck an A string, the string is going to start vibrating a little bit like this. And here's the thing from physics. It's actually going to be doing a little bit of this as well. And some of the physics and math are going to get a little gnarly, but I'll try to keep it under control for you. So you've got this, and an A vibrates at 110 hertz. The second harmonic, which is doing this motion, going to go twice as fast at 220. And it's actually going to keep going. So we're going to have a third vibration that looks a little bit like this. That is at 330 times per second, 3 times as fast. We've got 440 as well, 4 times as fast. All of these vibrations are going on simultaneously. And so when you pluck the string, it's really doing something a little closer to this. The magnitudes of each of these vibrations, whether it's 110, 220, 330, 440, all going to vary, different amounts of each, and that's really the difference in tone. You pluck a string, and the physics says the string's going to vibrate, and always going to do that, so whether it's a Les Paul, Strat, what have you. The trick is you get different amounts of these different frequencies, and this is where the different flavors, the different tones come in. You can think of it like a recipe. You get a little bit of ingredient A, a little bit of ingredient B, a little bit of ingredient C. The variation in how much of each one of these you have, that is what you're going to get in tone. So the guitar pickup is detecting what happens on the string. And as the string vibrates up and down, the red line is the string, the green line is the signal that gets sent off to the effects and the amplifier. That's what you're hearing, is the electrical signal picked up here. And if we switch where the pickup is, where we're detecting, say from here over to here, the signal, the green line that's going off to the amplifier, also changes. Now generally, neck pickups, bridge pickups, they're going to be wired a little bit differently. But really the tone that you're hearing, the tone of the guitar, very much dependent on the physical location, less so on the actual wiring of the pickup. And this is something people don't normally appreciate, but when you go switch from guitars from a Strat to an Les Paul to whatever you might have, pickup positions along the string are going to vary, and that's a lot of the tone. And so let me go give a demonstration. All right, so this guitar is actually one I built from a kit a little while ago. So I hacked it up. Don't worry, it's not like a classic Fender Strat. About an $80 kit I bought online, went out, painted in my backyard, put together. But basically a Stratocaster. What I've done is modified it a little bit. I hollowed out the area under the pickguard and then chopped apart the pickguard a little bit so that I can move the pickups around. So it's still a regular guitar. And so I'm currently on what would be normally a neck pickup position. And what I want to demonstrate here is the physical location of the pickup actually matters. So here's a low E. And A. Now I'm going to move the pickup. Come on. Here we go. A little bit of tonal difference. Pick up, top. And the point I'm trying to make here is where you are on the string, where the pickup is, that's a lot of the tone. That's going to determine a lot about what you're going to get out of tone. Same pickup, same guitar, same string, same electric, everything. The only thing I'm changing is location of the pickup. And if you go off and buy a guitar in the guitar store, okay, you just pull a Les Paul or whatever it is off the shelf. The thing is, pickup locations are fixed, and there's nothing you can do to change the electronics, change the pickups on a Les Paul that will make it sound exactly like a Strat or vice versa. It's where the pickups are located. All right, so let's do a little bit of the scary math. I'm going to try to move through this quickly and make it as painless as possible. There's a numerical technique called a Fourier transform, and there's a fast method for it, so it's the fast Fourier transform, or FFT. It's going to take the signal coming off the pickup, that's this green line, and work backwards to figure out what are the frequencies that make up whatever sound is coming in. And so if I play an A note, I've got a vibration at 110 times per second, also 220, 330, 440. So we can take this green signal coming out and work out how much do we have of 110, how much do we have of 220. And it's the variations in these levels that make the different guitar tones. So we wind up with a signal coming in, and then graph coming out telling us how much we've got of each one of these. All right, so this is where I want to try to tie the whole thing together as to exactly what's happening with the tone of a guitar. I've got Telecaster here again, and over on the screen here is actually a fast Fourier transform of what's going to come out of the guitar and go off to the amplifier. It's a signal from the guitar with the pickup. So you can sort of see the white line wiggling around here. And that's what's being detected by the pickup. Down at the bottom part of the screen on the left there is the actual component frequencies. So your A note vibrates at 110, 220, 330, 440, 550, on down the line. And so we're taking the signal that comes in, running it through a fast Fourier transform, graphing it on the bottom, and you can see all these peaks there. And you'll notice that around the 4th, 440, this peak not really showing up. That's because it's the bridge pickup. The string is vibrating. This spot right here, 4th harmonic, even though the string is wiggling up and down, not detected because it's not really moving on the 4th harmonic right here. That's why it sounds this way. I switch to the bridge pickup. Different harmonics, different component frequencies, still same pitch, same strings, whole 9 yards. Listening here versus listening here gets you a different tone. And this, if you hadn't thought about this, this is why same note, same whether A, B, C, whatever you got, anywhere on the fretboard, going to change the tone depending on which string you use. So we go back to the bridge, we go back to the neck. Here's an A, open A, 4th is sort of dropping out. I can play an A here, up on the 5th fret of the E string. Sounds different, and you can actually see the difference. Here, turns out 5th fret, I shorten the scale length of the guitar, so it's just vibrating from here down to here. This is about 1/3 of the total length now. 3rd harmonic dropping out. That's why they're different. That's the tone of your guitar. And so as you go from a Tele to a Les Paul to a Strat to whatever it is, pickup position is going to determine a lot of the frequencies that you get detected off the guitar. That is affecting the guitar tone. And so usually when you go out to buy a guitar, and they'll tell you about whether it's maple or swamp ash or oak or whatever, maple fretboard, I don't care. Doesn't matter. Whatever, man. Pickup position, huge part of the tone. Fingers, I'll do a separate video, but your fingers, also part of the tone. That's probably enough for today.